Okay, welcome to your lesson on galvanic cells. We'll get straight to the point. If you get two metals from the activity series of metals and you put them together, they will have a displacement reaction, where the one that's higher on the activity series of metals is going to force its electrons into the thing that's lower in the activity series of metals. And you can harness this process by, instead of just having them displace each other in a beaker, rather stick a wire in the middle and put a light globe on it, or whatever. Now I realise the lighting is not the greatest here, it's just a dodged up setup I've done at home on my desk. But let's get straight into it. This is called a galvanic cell. Galvanic cell. Now we're going to use two metals, zinc and copper. Now, these are the classics. If you look at any galvanic cell, it has the same basic setup in stage 1 chemistry. Now, have a look at zinc and copper on the activity series of metals, right up on the, what do you call it? Next to the periodic table. And you'll notice that zinc sits above copper in the activity series of metals. So zinc will force its electrons onto copper. If you were to put zinc metal into a solution of copper chloride, chlorine being the spectator ion, the zinc would force its electrons onto the copper would come out of solution and fall to the bottom, and the zinc would go into solution as ions. But what we're doing is we're sticking a wire in the way of this. So any galvanic cell always begins with two beakers. We'll have one here and one here, and we refer to these as half cells, and in them you put two electrodes and then you have solution. So let's say, for example, in this one we will have zinc sulfate, and it will be aqueous. And in this one we will have copper chloride. No, it's copper sulfate. And that'll be aqueous too. Now, this electrode here, because it's sitting in the zinc solution, we will make this the zinc electrode, and this one here, we're going to make this a copper electrode. Now, we join these by a wire, and in the middle of that wire, you can put an ammeter. I'm going to put a light globe, and then they join up like that. But this circuit is not complete yet, and I'll explain why a little later. But I think first things first, we need to understand the chemistry of what's going on here. Now, we know that zinc is higher in the activity series than copper. So zinc is going to take its electrons, force them down the wire, through the light globe, into copper, and copper's going to have to accept them. Now, when you've got your zinc sulfate and your copper sulfate in solution here, they're not sitting as zinc sulfate and copper sulfate. You've got two things that are in that solution, other than water. You've got Zn2 plus aqueous, and you've got SO4 2 minus aqueous. And this side here, you're going to have Cu2 plus aqueous and SO4 2 minus aqueous. But of course the sulfate itself is just a spectator ion, so we don't worry about that because it just does not participate in the reaction at all. You also have zinc solid, and over here copper solid. So you've got the copper ions in solution here, and they're all sitting around here, Cu2 plus, Cu2 plus, Cu2 plus, and you've got zinc ions here, Zn2 plus, Zn2 plus, Zn2 plus, and they're all floating around. Now, we've got to now look through to the half cell equations that are going to occur here. So I might just remove this zinc sulfate here and this copper sulfate here, give me a bit of space. Now zinc is higher than copper on the activity series of metals, which means that it can force its electrons onto copper, which means that zinc is going to oxidize, because oxidation is lost from oil rigs. So you're going to get this occurring. The zinc electrode Zn solid will become Zn2 plus aqueous plus 2E minus. And those 2E minuses, E minus, E minus, they're going to go down the wire here, and the zinc that was originally solid in the electrode is going to come off and become a Zn2 plus in solution. Now those electrons are going to travel down the wire to the copper. And of course that's going to create an excess of electrons on this electrode here. Now what that's going to do is force the electrons onto copper ions that are in the water already. So you get your Cu2 plus aqueous plus 2E minus makes Cu solid. So as it turns out, this copper here becoming out of solution and onto the electrode, it's actually going to plate. So this electrode will degrade and get lighter over time, and this electrode will start to plate and get heavier over time. But of course, in any situation like this, you need to have a circuit connected. For example, there's no connection between here and here, so you have to complete the chemical connection. And this is the last thing that we add to the galvanic cell, and it's called a salt bridge. So that's normally drawn like this. It will be a glass tube as such, some kind of medium, and inside it will be two things that won't participate in the reaction. Let's use sodium chloride for example, NaCl aqueous. So that's going to be Na plus and Cl minus in solution. And they are actually able to move. Because they're in solution, they can migrate either way through the pipe. So this is the chemical connection of the electrical pathways that occur. Now here, when the zinc solid is coming off and becoming Zn2 plus and 2E minus, and it's going into solution, this whole beaker is becoming more and more and more and more positive. And if you've got any physics education, you'd know that the more positive something is, it doesn't want to accept more positive charges into it, it repels them. It doesn't like that. So what the chlorine does is all the chlorines travel down the salt bridge, Cl minus, Cl minus, and they go into solution here. And they backfill as the zinc makes that beaker more and more positive. And all DNA pluses will go down and they will backfill for all the coppers that are disappearing out of this solution here. So that becomes balanced at the same time. And it's the salt bridge which connects the chemical pathways. Now what we're ending up here with is a set chemical process where Zn solid plus Cu2 plus 2E minus becomes Cu solid plus Zn2 plus aqueous plus 2E minus. Now, what am I missing here? This is aqueous here. Now, of course, you can cut that, and you just end up with zinc and copper aqueous ions going to copper and zinc aqueous ions. And by sticking this wire in the way, you can actually cause it to harness the electrical reaction itself. But wait, there's more. I'm going to give myself a bit more space here. In fact, let's write this whole thing out. Right, let's see how quickly I can draw this up. 1, 2, electrode, light globe. This is zinc, this is copper, salt bridge with NaCl. Okay, that's a pretty dodgy setup, but I'll connect the wires. Hold on, there we go. Now the circuit's connected and everyone's, oh, I forgot solution. Okay, there's a zinc sulfate solution and there's the copper sulfate solution. These electrodes have terms. Electrode refers to both of them. But as it turns out, they actually have names. So you've got the anode and the cathode. Now there's another, what do you call that thing, what the words are, and then they help you remember. Let's see, is it going to work? Up here. Can you see that? Yes, you can see that. An ox and a red cat. Anode, oxidation, and a red reduction at the cathode. An ox and a red cat. So that goes along the lines of, it's the next one after oil rig. An ox and a red cat. Anode oxidation and reduction at the cathode. And a reduction cathode. An ox and a red cat. Anode oxidation and reduction at the cathode. Just put it there. Makes it sound right when it's an ox and a red cat. But then when you say anode oxidation and a reduction cathode, it sounds ridiculous. But it'll help you remember it. Now, of course, remembering here, Zn solid became Zn2 plus 2E minus. So via oil rig, oxidation is lost. We can see that this is oxidation. And via an ox and a red cat, we can see that anode is oxidation. So this is called the anode. Whoops, can't even see that. Right. See, I wrote anode here. I wrote it really badly. You can barely read it. Now, here the copper is Cu2 plus aqueous plus 2E minus makes Cu solid. So you've got reduction occurring here, and based on NOx and oil rig gives us reduction. Then you've got red cat, reduction of the cathode. So this is called the cathode. Anode, cathode, and ox and red cat. Now, there's more. Let me show you. So that's how to name the anode and the cathode. Yes, oh yeah, positive and negative terminals. Which one is the positive and which one is the negative terminal? Well, in this case here, electrons flow towards the positive. So we label the copper positive because the electrons are going this way, and we label the anode negative. So in this case here, the cathode is positive and the anode is negative. I guess that's easy to remember because cations are positive. You know, you think of cats and you're very positive about them. So cathode positive. That's going to change, by the way, when we get to later parts. Okay, let me rub this out. The last thing you need to know is cell notation. So after drawing them, you can actually represent this entire process by doing this. Zn line Zn2 plus aqueous double line Cu2 plus aqueous line Cu. This is called cell notation. Up here you write NaCl, aqueous. So this says that you've got a zinc electrode going to Zn2 plus and a copper 2 plus going to copper, with a salt bridge, which is represented by the double lines here, and your sodium chloride, which is the salt in the salt bridge. So that's one half cell and that's the other. Now in the test you'll actually get something like this, and you have to draw an example. So I don't know, let's choose I'm sure you've heard of a NiCad battery before. Having said that, I'm not entirely certain which of these nickel or cadmium is higher in the activity series. So just give me a second. Activity series, metals, images. My computer right next to me. Let's have a look here. Nickel. It's there, and hopefully cadmium is not there. Great. Okay, let's have a look at zinc, copper, nickel, come on. I can't actually find where cadmium is. Oh, this is so frustrating. Ah, stuff it. I'll just give you something else. So why don't you try and make a battery out of Cu copper, and let's use another thing, gold. A copper gold battery. Now that's not going to be, you know, the cheapest battery. So what I want you to do, I want you to go all the way through to draw it, label everything, show a minus direction, I need more space here, more space. Do half equations, show cell notation, and show flow of all ions. And just for the hell of it, let's make the salt bridge potassium chloride. So you've got to show the passage of the copper, the silver, the potassium, and the chlorine. So if you can go through all of that, give that a shot. I suppose I'll do up the answers and stick it on Edmodo. Thank you and have a wonderful evening.